Let me pull it up. All right, same as always. I'll have the comment box open. Just remember that later today, at some point, I'm not sure what Nathaniel said about due dates. Today, at some point, the lab is due. And just send it to Nathaniel to his email address before the day is up. If he's given you some specific instruction, that instruction trumps mine, what I would say about due dates and formatting and where to send it to. But today, Lab 1 is due to Nathaniel, to his email address. And we're going to get into a bunch of the regression stuff. That's what the next lab is going to be on, is a bunch of regression. And you'll make another table 1. You'll do all that stuff again. And that one will be due on October 16th, which is sort of soon. So Lab 2 is coming up. So you don't want to put it off for too long. You can do this thing. Lab 1 takes a long time because you have to get SPSS and install it and figure out how to use it and how to open and run these things. And so the learning curve is part of the time of Lab 1. Lab 2, it's already installed. You know how to use it, and the learning curve is finished. Lab 2 is the most time consuming of the labs, probably. But you can still do it in a day. I mean, you can tonight, you could do the entire lab. I'll show you how to do the bulk of it, and you should be able to do it in one day, in one night. The readings, no new readings, the assignments, just remember the countdown. So lab 1 is due today, and then on the 14th, the research topic is due. And then we start having a bunch of due dates as we get into October and November. There's a lot of due dates, less and less reading if you're into that. If you decide to do the reading, there's less of that. Here's what to send me, right? So one person has sent me the CE-cert so far. And actually, I know one other person in the class has already done it, and so wouldn't have to do it, just resend it to me. But your name, there'll be this little thing, your name will be there, your email address will be there, your scores will be along this column. And remember, so this is somebody's from 2017 that I've taken the name off, but remember, you can redo all of these modules. You can just redo them until the very last one where you can't redo. And so you look and it's like 0 for 5. I think somebody was going and then realized that was the last module and you can't redo that one, and that one saves. But whatever the minimum score is, something like 80% you have to get to pass the whole thing. I've had people fail it, and I'm not sure how that happens. Not every year, but every once in a while somebody fails it, like, man, I bombed the CE-cert. Like, what did you do? You can retake them. You click submit. It says, here are the answers, here are the questions, and here are the answers and what you got right and what you got wrong. Would you like to retake the module? Obviously, you just go back and take it again and click on the right answer. So when people fail the entire thing and like, I bombed the whole test, it just baffles me when that happens. But usually I'll see this at the very end, which is like 0 for 5. Somebody who gets, the 5 for 5 on the last one means they're actually doing it and paying attention. You can also just copy and paste all of the text into a Word doc and then do a Control F search for whatever the question is. That's another way of doing it. Where it'll give you this big reading and you go through that, like you just highlight the whole reading, copy and paste it into a Word doc, and then go take the module, and then whatever question it asks, just look for the keywords in the question, Control F, and the thing, you should be able to find it. So it's not that hard to go through it, but just send me that completion form, that PDF completion form. And the IRB forms, I don't have anybody's yet. You know where to do it. This is the website for Pacific that talks about IRB and HIPAA and all that stuff. On Canvas, there's the IRB stuff. And just remember the poster topic things. These are sort of coming up. All of this is coming up sooner than it seems like. Oh, don't worry. If like to those of you whose like camera isn't working, I'm seeing comments. Don't worry. The publicly accessible data that you can just go on these websites and find. Remember, all of these things are opportunities for your research project. If you can't come up with a question, just go browse what data exists. I'm like, oh, that's kind of interesting. And then that becomes your research question, right? That becomes your topic. Just because you found an interesting database, you now have a research question and data already. Now, if you come up with your question ahead of time and then have struggles encountering data or acquiring data, you're going to have to change your research question, right? Data have to be available. You have to be able to somehow analyze stuff. And if your research question is, well, I'm going to do, test athletes in this particular domain, you probably COVID outside, right? You probably don't have access to do that. And so I would start trying to figure out what data are available and factor that into your research question. And again, this is a great website, just tons of stuff if you want to be in health. But whatever, you can just type in publicly accessible data in Google, and I'm sure you can find publicly accessible data. MLB. We published one student, I may have mentioned this earlier, JP. Some of you know JP. He just transitioned into the master's program, and he published and presented his HESP 180 project. It was about Tommy John surgery, and he just the backs of baseball cards. And I mean, not he wasn't looking at actual baseball cards, but you just go on the internet and you can find publicly accessible data on every single performance statistic from the beginning to the end of every player's career and their salaries. And you could say, what determines a professional athlete's salary, in basketball or in baseball or in hockey or something? What performance metrics? Or you could say, JP's was, does Tommy John surgery ruin post-surgical return performance? And the answer is pretty much no. It just prolongs careers. It's the title of the project was something like quantity time over quality time, something like that. But data exists everywhere, but you have to get data. The project isn't just analyzing someone else's study, it's your own study. You have to do your own analyses on data. Now, someone else can collect the data, someone else can build a database, but you have to do your own analyses on that database. You have to open it up in SPSS and have your own findings. And sometimes the acquisition of data can be a little bit challenging. And so using some of these resources just to find publicly accessible databases can help guide a research question. And as we move forward into the posters, your title is due. It's just keep this stuff in mind. It's the lecture 1, lecture 2, these contents of what is science, why is science important? How are we communicating these things? This should be the governing philosophy of how you conduct yourself in the scientific world. And the purpose of research, what's a good place to start, a good research question, communicate very clearly to where a 10-year-old will understand with enough explanation of fundamentals. But keep this stuff in mind as you move forward with your research subject, your topic, and use these labs, right? Go through these labs and really start to understand how to run these analyses, because every analysis you see in the literature, when you're reading some journal entry, every analysis you see is almost all of them, probably all of them in the course of your life, will be stuff we cover in this class. And there's some other analyses that we can talk about. We can get into those outside of class, or if you decide to pursue epidemiology, public health, if you want to be a statistician, it's probably the highest paid job any of us would be qualified for. It would double my salary if I decided to take one of those jobs. So if you want to go into this field, you're really learning everything you need to know in this semester. And if you don't want to go into the field, just get by on the tests and kind of learn little conversational bits as you go. Totally fine. But if you do want to understand literature and science and how we know what we know and how to contribute to the body of knowledge, understanding this stuff is pretty critical. So make the most of your labs. Just remember, in SPSS, there's variable view, there's data view. Data has all the data in it, right? And frequencies and descriptives, right? Descriptive statistics, frequencies, descriptives, that's how you're going to go to this descriptives, and that's how you're going to get the means and standard deviations, drag all those over, hit OK. right? So there's your descriptives. For frequencies, right, drag over like dominance, like left-handed or right-handed or whatever. And did they get a personal record? Yes or no? And sex and political party and whatever. Frequencies, percentages, drag them over, hit OK. And then now we have this, right, for table one, the total column. And then t-tests, right? We're doing t-tests. Now, if this is baseline and this is follow-up, and this is like mean of the total or something like that, that would be a paired samples t-test. But almost always in table one, nearly 100% of the time, what you're going to see in table one is subsample comparisons. Unless you really discriminate in your enrollment, right? If it's just, okay, we're just looking at males age 19 who are currently enrolled with a 12 exactly units. I mean, if you really narrow your inclusion exclusion criteria, all right, maybe you're not going to have subsamples for you. Even then, you could have subsamples. You could just say people above the mean, people below the mean in some particular variable. You enroll all those people, and you could say, well, people who are above the mean and below the mean in BMI. You can pretty much always come up with some sort of subsample. But subsample comparisons, these are going to be independent samples. T-tests, remember William Seeley Gossett, that's our T-test guy. What the T-value means, signal to noise, the signal being a difference in means, as long as you know noise is just scatter, right? So you don't need to know this actual part of the equation. Know this part of the equation, the difference in mean values of these two groups. Because a t-test you can only do on continuous data. You can't do a t-test on categorical data. So on continuous data, you're going to have a mean. There's going to be a mean of continuous. It's GPA, it's body weight, it's whatever. It's dollars, it's BMI, it's height, it's grams of this or that, it's pH, it's whatever. All these continuous variables, they're going to have a mean. And so in a t-test, you're comparing one mean against another mean, not one mean against another mean against another mean, right? You're getting into ANOVA there, but one mean against another mean. One group's mean plus or minus standard deviation compared to another group's mean plus or minus standard deviation. So the difference between means, that's the signal in a signal to noise ratio. The noise is down here. You don't need to know that formula. But remember to run your t-tests, compare means, independent samples t-test, if you're doing an independent samples t-test, and then you get an output like this, right? So males and females and power, watts, how many watts are producing, and I can't remember what exercise this is. It's some press or something. And what the range of motion is in three-dimensional space. How far does that bar path move? And the consistency of repetitions. If they're doing, say, 10 repetitions in a row, I mean, down to a few microns, right? What's the replication rep by rep? How closely do they move? Does each rep correspond to the next in terms of that three-dimensional space? So pretty close, 82%, something like that. But the significance over here is what you report in the table. So consistency is the same between men and women. These are different between men and women, meaning power and the range of motion in this sample, right? Resample, take a bunch of other subjects and test them, and maybe you'll find something different. And that's where you start to look at the 95% confidence interval of how sure are we that the true population mean, so here's the mean of the exact mean of our study for men. But what's the, if you get into the 95% confidence interval, what do we think the true population mean is? Over here, we're looking at true difference of the population mean. So there's our t-tests. Put your significance, that p-value in the last column. For these, remember, it's going to be chi-squared. So descriptives, crosstabs, and then you just drag over say sex, or drag over whether somebody did tutoring, or drag over whether somebody did the CD cert or whatever into this column, and then whatever other categorical thing into this column. The statistics button is what you're going to, so this one's sex and astrological sign, whether they know it. So male, female, coded as 0, 1. Do you know your astrological sign? 0 is I have no idea what the hell it is. 1 is I know for sure, I read my horoscope this morning. And then you click on the statistics. Remember, click on chi-squared, and then hit continue, and then you're going to click on the cells box and do the column, hit continue, and then hit OK, and you'll get your outputs, which are going to be the percentage differences and the corresponding p-values for the subsamples. So that's what's due today for your lab. And then, but remember, if you're going to do a correlation coefficient, you're going to compare two variables, do two variables move together. The Pearson correlation coefficient, that's what we keep talking about. That's your R. That's two continuous variables moving together, two continuous variables and the correlation between them. A point biserial correlation, one of those variables is dichotomous, male, female, Democrat, Republican, if it's like a two race, two ethnicity, division, something like that, athlete, non-athlete. One variable is dichotomous for a point biserial, and the other one's continuous. Phi or phi, this one is dichotomous and dichotomous. So it's males and females and athlete or non-athlete. So looking at correlations, not cross tabs. So you're not doing these chi-squared p-value differences. You're looking at correlation, so it's a little bit different. And then Kramer's V, categorical to categorical, but not in a 2x2 table. And it is, we're looking at, again, correlations, but not in a 2x2 table of this categorical. So what it's going to look like, right? Positive correlations have a upward slope, negative correlations have a downward slope. So it's positive as one variable goes up, the other variable goes up, negative as one variable goes up, the other one goes down. So that's what it means. Now the correlations, so I go to equatorial Africa sometimes. And this is where, if I go to Uganda, I've gone to Uganda a couple of times, this is where I live, right? I go to the Makerere Flats. And you get somewhere new, and the first thing you do is you try to survey your surroundings. All right, where am I? Where's the grocery store? Where do these roads go? Where are my surroundings? Like you're taken hostage somewhere. I'm not taking hostage. Like Uganda is like one of my favorite places in the world, but well, let's say you're like taking hostage, like blindfolded, you're in the Jeep driving along the dirt roads, bumping around, and then you get out and you sort of look around. You have no idea where you are. You're sort of looking around. This is how you analyze data at first. Now, the first thing you do is like, all right, let me describe my immediate situation. Here's the people, here's me. So that's your table one. But your correlations are doing this. Your correlations are giving you this bird's eye view, this satellite kind of Google Earth view of your surroundings. Now, they're not telling you, when you do correlations, it's imprecise. Correlations are imprecise. It doesn't tell you what the grocery store sells. In this case, Tuskie's. That's the grocery store I go to. So in this case, it doesn't tell you what Tuskie's sells. It doesn't say what all the businesses are. It doesn't say, how many cars are on the road. It doesn't say the climate. It doesn't say anything about the language. It doesn't say, all the details are totally missing from a satellite image. That's what a correlation is. A correlation is just this satellite image of your data. You're dropped into this landscape and you sort of look around and say, okay, I see mountains, I see a road over here, this part is grass, this part. It doesn't give you a level of detail, right? There's no clarity in anything, but it starts to draw a very crude map and it gives you some direction. You now know what roads are there. That's what correlations do. You throw all of your variables and many of your variables, the variables you care about, into your bivariate correlation table, and it spits out all of these correlations, and that guides your exploration. From that point, you decide, you know what, I'm looking at, there's a lot of activity over here. I'm going to go explore this at ground level. Now, ground level is we're going to run a bunch of regressions, linear regressions, logistic regressions. We're going to do predictive modeling, more sophisticated, precise statistical analyses. But you don't really know what to do with your regressions until you run your correlations. Run your correlations, say, oh, it turns out this doesn't matter, but look, this is fascinating. Now, you have to use your brain a little bit to say, is this fascinating by random chance, or is this fascinating? Like, that's something I actually would expect, or there's something I don't think this is random. I think this correlation is actually potentially meaningful, right? Because what you don't want to do is just explore every spurious correlation that doesn't matter. Um, if on Google Earth, sometimes it's like blurry somewhere. It'll be like a blurry spot. You're like, I don't need to go explore that. I don't think there's like a misty, like Stephen King environment over there that's covered with everything's blurry, right? You just assume that there's like spots, that they're just error spots. But you assume this isn't an error spot, right? You got to Wanda Gea. That's not an error spot. That place is awesome, by the way. But and so you correlations are bird's eye view. It's satellite images. There's no detail. There's no real understanding of the landscape. You have to get on the ground level and walk around and explore, and that means regression. Okay, so there's a question. Can you repeat what a point by serial correlation is? Yes. So when you're doing your correlation table, let's actually get there. So I'm going to explain what that means in just a second. But this is just me saying exactly what I summarized, right? You see what roads exist, but you don't really know what's on the roads. You don't know, what the people are like. You don't know, are the plantains good here? Should I go up the road? That stuff is regression. Um, so to do the correlations though, topical satellite imagery, again, right after I build a table one, my very next thing, 100% of the time, my very next analysis is to do this, to get a sense of my surroundings. And so analyze, correlate, bivariate, two variable correlations. And again, you get this huge table. Now, the question, what a point by serial correlation is, if you have continuous to continuous, which is what all of these are, right? You just drag this down. Diastolic associates with age. Diastolic associates with pulse. Diastolic associates with systolic. Diastolic associates with diastolic, obviously, that's not a thing. Diastolic associates with mean arterial blood pressure, should be, because it's 2/3 of it. But so, and you could do the exact same thing going from this direction. Diastolic associates with age. So you expect this right here, again, to be the exact same as this right here, because age to diastolic, diastolic, to age. Well, you get what I'm doing. So diastolic over here. Now, what is going to calculate all of these are Pearson correlation, Carl Pearson, the Pearson correlation coefficient. And negative means inverse relationship. As one goes up, the other goes down. Positive means positive relationship, direct relationship. As one goes up, the other goes up. The strength of the correlation, one is perfect. You're not really going to see that. You're going to see something. This is really high because mean arterial blood pressure and diastolic blood pressure. I mean, like, diastolic is part of the equation. It's the bulk of the equation. So we're getting pretty close to one there when diastolic is the equation. And but when like a point by serial correlation, it's the same thing. It's correlation, but it might be males and females and salary or something like that. Dichotomous and continuous. Continuous would be salary, or males and females and height, or your BMI, or males and females and grams of glycogen on board, in your muscle and liver and stuff. That is a point by serial, and that's the same thing. It's going to calculate your point by serial for you. So it'll say Pearson correlation coefficient. But if you put a binary variable in there, if you put sex in there or something, then it's gonna do that calculation for you. And that's a point by serial correlation. May you please go over with the asterisk? Yeah, the asterisk and the two asterisks. That's just a flag. That doesn't mean anything statistically. It doesn't mean anything that you would report. What it means is look at me, look at me, look at me. Now, maybe what would be even better is if they just color coded it. Red is less than 0.05, a p-value of less than 0.05, and flaming yellowy orange is a p-value of less than 0.01. That's all it's saying. So one asterisk is saying there's a p-value of less than 0.05. Where classically that rigidity, Fisher stuff were significant. A p-value of less than 0.05 or significant. Two asterisks. We're highly significant. A p-value of less than 0.01. So 99% sure. Right now, it's, again, if we're going to do the kind of crude colloquial version of significance, we're 99% sure is a p-value of 0.01. But the full version of a p-value, let's do 1. Where's a p-value that's like 1 asterisk? Not many, because there are so many subjects. Okay, here's one. Mean arterial blood pressure and heart rate. So as mean arterial blood pressure goes up, this is positive, the R, the Pearson correlation coefficient is positive. As mean arterial blood pressure increases, so does heart rate, pulse, right? So does heart rate. And there's a p-value of 0.024. So if the null hypothesis is true, meaning heart rate and mean arterial pressure have nothing to do with each other. That's the null hypothesis. No relationship with each other. Totally arbitrary, totally unrelated. Then there's only a 2.4% chance, a p-value of 0.024, a 2.4% chance that we would have observed a correlation this strong or stronger if that null hypothesis is true. So the rows are the independent variables, right? Columns dependent. No, it doesn't matter. Everything's everywhere. So every single row has, age, pulse, systolic, diastolic. Every column, age, pulse, systolic, diastolic. Don't worry about independence and dependence here, because they're just correlations. Do these two variables move together? Now, what you want to do, a little trick, when you're dealing with big data, big databases that have, let's say, 100 variables in a data set, what you want to do when you run your correlation table, put the these first few, when you're loading up your correlations, dragging them into that box before you hit OK. Put the variables of interest there. So in this case, like, you would want to look at, let's say that there's another 100 variables that continue off the screen, and it's stuff like, actually there is in this particular one, I just copied and pasted some of it. But you can scroll down and scroll down and scroll down and still see what variable it correlates with. But if you scroll across, this ends up missing. Play with that. You'll see what I mean when you do this in real life, right? When it's not just on my screen and this is an image. But you can scroll down and scroll down and scroll down and still see, you just know this is age and this is pulse. And you sort of scroll down and look for stars and just keep scrolling. And then when you see a star, you look over and see what it was. Keep scrolling, keep scrolling, keep scrolling, look over, see what it was. If you scroll to the right, you have no idea what these things are over here anymore. You just sort of forget them. So if you put the first few in right here and just memorize those and just scroll down, 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 it's easier to monitor that way. Okay, so interpreting correlations, there's a question about, how do you interpret these correlations? Correlations are very crude. Really, they don't matter. You don't report them in a final draft. You so seldom report correlations. If you see somebody reporting correlations in the literature, most of the time, that means that person doesn't know statistics, because there are more compelling statistics that could be run, more compelling analyses that could be run. So you begin with bivariate correlations to give yourself ideas. You don't put them in the final. Now, sometimes you will see basic correlations in the final, and that's okay conditionally, rare conditions, but there are conditions, there are study circumstances at which you put these in as a final statistic. Fine. Usually you're going to move on to something better, and this just informs your decisions. Okay, so remember GIGO. Let's pick up where we left off last time. We'll warm up, right? We'll do a warm up lap before we get to where we left off. But remember, people make mistakes. Now, sometimes that's accidental error, right? We have accidental error on occasion. And so we think we're giving MDMA to a bunch of monkeys and we're really giving them amphetamine and that's why they're dying. That was an accident, right? And that article was retracted. You can still find it. It's still of value, but that was an accident. Now, accidental error and deliberate error, accidental error is fine. You're going to do it. Try to do it as little as possible. If you can avoid mistakes, please do. If you're going around and most people don't mean to get in traffic accidents, that nomenclature alone should indicate that it was an accident. It's like, oh, I hit this person on purpose, right? That's just very rare when that happens. But still, you shouldn't get in traffic accidents all the time. Be more aware, be more mindful, put a little bit of thought, quit being so distracted, or whatever it is causing accidents. Stop it, right? Use your brain a little. But we're still, even when you're paying attention, we all spill milk. if you drink milk, whatever. We all spill, it's coffee, let's say, we all spill coffee. Um, we all break a dish now and again. We all have, some sort of mistake that we make, and that's okay as long as we're not accident prone because we're lazy. Deliberate error, these are the assholes, right? These are people that you want to exclude these people from your life, and you hope they don't have a chance to vote. And I mean, these are like the deliberate error people who are just sort of like ruining the world. um, I mean, Alex Avery, if like there are people where you just like, man, I hope hell exists. It's like those are the deliberate error people. And certainly don't do that. Avoid accidents where possible. Don't do deliberate errors, because then you're just like a piece of shit, right? I hate the deliberate error people. I get to these and man, my heart rate goes up, and I'm like, why don't we have more like prison space? So now lab 2, this is what we're trying to do, is figure out where error lives where we don't always see it. Now you can say like, okay, people don't put tanks over the terrariums and the frogs jump back and forth and they all die, and then we pretend that that particular pesticide is not hurting anything, and let's keep using it, and for the billions, right? Let's just keep using it for the dollar. But then when you get into the gun argument, this is nothing that Hulk Hogan ever said. I just needed to put somebody there talking. But don't do that thing where you get biased, right? Allow the stats to speak for themselves in every argument. I've just watched the presidential debates. It's painful, but watch them. And as soon as somebody raises their voice, that person's losing the argument. You can't be passionate in an argument and still win. It almost never works. Unless the other person cowers or something. But as soon as somebody really starts raising their voice and the veins pop out, or that person has sort of lost the argument, and why else do you need to shout? The truth doesn't need megaphones and shouting and giant, like jugular, activity. The truth just needs to be declared. We don't need all that passion behind it. And so be dispassionate in everything you do. Now, let's talk about the way people argue this stuff passionately. The gun right. People are so uptight about this. Many people, not everybody. I mean, most of you probably say, who cares? You shrug your shoulders as much as I do. But, I hear arguments about the Second Amendment. And again, I don't care. Every single person, we could have 800 billion guns in the US, and that's fine. I don't care. That's totally fine. But I hear people shouting about the Second Amendment. This thing was adopted in the 1790s, right? This has nothing to do with today. That's like the bayoneted musket was advanced killing technology back then. It's not describing anything that we have today. At this time, we had people wearing powdered wigs who thought the whole world over could be used for local farming. What does that have to do with today? None of the 1790s is compatible with today. And so as soon as somebody says Second Amendment, I assume that person didn't graduate middle school. Where like in middle school you're supposed to learn that stuff. And then the argument of like Switzerland versus Honduras, I hear this all the time, and it's so ludicrous. So when you start making these comparisons, you'll hear it on the news. That's what I'm talking about. I'm not talking about like I'm on campus and people are making this argument. I hear it on the news after every school shooting or gun crime or whatever, where like an AK is misbehaving and like the person's hand. But people say like, okay, Honduras, population of 8.2 million, they ban citizens from owning guns. They have the highest homicide rate in the world. Compare that to Switzerland, population of 8.2 million, requires citizens to own guns, lowest homicide rate in the world. Now, this is among the most misleading comparisons that has ever been drawn. So Switzerland, let's just start with the basics. Think type of people who, think context, think confounding variables. You don't just accept relationships at face value. What is the explanation here? Now in Switzerland, like every man, at least, for women, it's voluntary. Every single guy has required military service, and they're issued a gun and bullets, and the government keeps tabs on every bullet that they're given. And so it's not like you're going out with like free shooting sprees and stuff. The US has less regulation than Switzerland does in terms of, this is like one of the most regular, yeah, you're issued a government gun and government bullets, and they keep track of every bullet, every at least government issued bullet. Crazy regulation over here. And so pretending is like, oh, this is just free reign. Everybody has 75 guns and they just shooting everything. Like that's not even close to true. This is like highly regulated. And then over here, The reason that they started enforcing all of these stricter firearm laws is because until 2007, and so until fairly recently, you could just openly carry firearms in public. You could just walk around the avenue, right, with like guns slung over your back, and just gun crime was outrageous. It's like, we got to do something about this. Now, ban, all right, this isn't quite true, but there are stricter regulations now because of all the killing. And it was sort of just like a free for all, and then all the killing. And so, making this comparison is probably the most, people talk about apples and oranges. Oh, you're comparing apples and oranges. That's fine. There's a bunch of, it's like they're both fruit. They both grow on trees. They're both, I don't know, in the same area of the color spectrum, right? They both have comparable sugar. The vitamin mineral profile are similar. I mean, like, it's fine to compare apples and oranges. That's totally fine. I mean, you're comparing apples and aliens or something. I mean, there's like, it's so ludicrous. And so all these arguments people make, and they're so their volume is so outrageous. We all need to calm down with this stuff, and that's what lab 2 is about, is calming down and allowing numbers to inform us, right? Allowing science, where possible, to inform our beliefs, to inform our behaviors, the sentences that follow. Now, this is better, right? Domestic violence homicide rates drop with stricter gun law. But what they say, like, when domestic violence offenders are required to relinquish their guns instead of simply being barred from owning guns, the risk of these offenders killing their partners goes down. That's a very, very specific group, right? This is when you talk about internal validity, external validity. This might have decent internal validity. Now, where was the study done, right? What was the study done in Houston? Was the study done in LA? Was the study done in Providence? Like, what district are we talking about? And what types of domestic violence are they? Repeat offenders, and everything from tax bracket. I mean, like, this may have good internal validity, but external validity, generalizability, who can these findings be relativized to? Only this group. You can't just say guns lower crime or guns increase crime, I guess, for this one. So get rid of guns and crime goes down. You don't get to say that. What you get to say is narrowly frame a specific population with specific circumstances in a specific region, and say, under these conditions, with this particular group of people, and this exact enforcement, we do see murder rates going down. You can't say, like, well, guns are bad. You don't get to say that, right? And so this article is okay, but what people take from that is often so ludicrous. And what we have to do for this class, the whole point of going through a lot of this scene setting, right, is to give you, where does this stuff apply? And you can encounter, just keep your eyes open and be mindful of the different conversations and arguments that are happening all around you, on the news, on campus, on Instagram or Twitter or whatever, and be able to dissect those arguments. And almost always, not always, but almost always, what you get to say is nuh-uh. And then you have the real argument there, because most people don't understand science and how mathematical probabilities and logic and reasoning work. And so you do, right? And by the end of the semester, you'll have this really comprehensive understanding. This is just, you don't need to know anything about this. This is just a conversation with my friend Fred and I. We were texting back and forth back in 2016. And that's when I decided to do this gun lab. Lab 2, which you're going to do, is in 2016, because there had been, in the last couple of weeks before this happened, late January, early February, there are 4 school shootings. Now, the first couple, the January ones, weren't particularly serious. The February ones had increasing victimhood in those ones. And what I wasn't sick of was the tears of the victims. I was not sick of the sorrow, the disappointment, the anger. I was not sick of the emotional turmoil, the commentary about how do we improve this. What I was sick of is people who thought they had answers when they don't, and people who are so they just insist that they have the answer, and they know less than the people they're talking to. As soon as you start making that insistence, you are telegraphing that you know less than your audience, and why are you the one talking? And so that's when this is what I sent to my friend Fred. Fred he's this really smart guy. He went to Princeton and Stanford and Oxford got into, whatever. But you can look him up. Just type in Fred Frank Jeopardy. He won a bunch of Jeopardy episodes. But that's whenever I have these, I'm like, I'm so sick of this. I usually text Fred. But so it was 2016 is when I decided to do this. And then after 2016, this theme of pro-gun, anti-gun, and the almost violence of the argument has not slowed down. So what you're going to have to do, 3 possible findings, right? You're going to have to find 2 of the 3, at least these 2. And then if you want to do this one, please have at it. It's super easy. That's like almost everything, but at least do those 2. And this is where we left off with John Lott, really smart guy. He looks, again, dangerous or suspicious, or like, if you're the mother of somebody and this guy comes to your door, like, I'm here for, like, but he's a really smart guy, very articulate, this UCLA PhD in econ, smart guy. But when he talks about this coincidental, coinciding, right? When he says coincide, this means coincidental, where handgun permits. All right, let's increase the amount of handguns and we're decreasing crime. That's the same coincidence as saying Miss America is killing people with vapors, with steam baths and stuff. It's very coincidental. It coincides, it correlates, right? But that's not a story. That's not causality. And then the original analysis, right? So if we're doing a logistic regression, which we'll get into next week, a logistic regression is the odds of something happening. And so what are the odds that we can create a female? Well, if you are younger and so if 0 is female and 1 is male. So as we get older, we are more likely to be male. As we get taller, we're more likely to be male. As we weigh more in this study, we're more likely to be female. And so these are all significant predictors of whether somebody is male or female. So just get older and let's see what happens. What are your chromosomes doing as you age? Like, that's not real. That's not an analysis. Now you can do it. This is statistical significance. The unstandardized beta, right? So this is your effect size, and then actually over here, this is your effect size. This is logistic regression. This is your exponentiation of beta in a linear regression. To be over here. So over here we have our exponentiation of beta. So this is the effect on the odds. So as you get older, the minus sign means it's small. The odds that you're going to become a male go down, and or become a female. Odds you become a female go down. And so it's hard to read these things because it's so gibberishy. Like, it doesn't make any sense. But statistical significance and our odds ratio and our 95% confidence interval and the Nagle-Kirky R squared, that's a pseudo R squared. You're sort of explaining a type of variance, a type of scatter here. But the model is totally gibberish. Like, the model doesn't mean anything. And so in addition to that, this is something that just from the National Academies of Sciences, you have the initial model specification when extended. This is talking about the gun control and violence. When extended to new data, does not show evidence that passage of right to carry laws reduces crime. The estimated effects are highly sensitive to seemingly minor changes in the model specification and control variables. So what that means is you just control for something else and the effect goes away. So remember, age was a significant predictor in the last model, which is this one. So the odds of being a female go down as you get older. But if you just control for a sport somebody plays, it's no longer significant. P equals 0.585. And so the odds here get totally changed when you control for sort of an arbitrary thing. And this is what people are doing with the gun database. This is where you can sort of make any claim whatsoever and come up with statistical significance. It's bullshit, right? It doesn't mean anything, but people are doing it. And then they get on the news and make these bold claims with veins in their necks. And you will know that it's just silly nonsense. So there's a nice one. From, I don't know, 2003, I guess, when it came out, where it's just talking about the test of time, right? So going back to Lott's article where he says between 1977 and 1995, in some very particular districts, some very specific districts, between these specific years, we see this effect happening, that you increase guns and you're going to decrease violence, decrease guns and you increase violence over specific years and specific regions. Now, remember very early in the semester, maybe second lecture, third lecture, something like that, we talked about the Super Bowl indicator. I don't bring this stuff up just for like a giggle. Remember this thing where we were talking about who wins the Super Bowl and does that predict the stock market over the next year? And for a long time it did, right? Between 1967 and 97, 31 Super Bowls, it was accurate 28 times of who wins the Super Bowl. And it's like, does that determine whether it's a bull market where we're doing well, or a bear market where we're tumbling and collapsing? Now, after 1997, consistency is sort of silly. It's 9 true predictions and 13 false ones. It doesn't really matter. But if you look at like NFL, NFL, AFL, NFL, 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 tons of NFLs, right? And what we're predicting is the stock market increases. Almost every year, the stock market's increasing. It doesn't go down that often, right? The stock market doesn't go down that often. But so if the NFL or NFC, if they're winning the bulk of the time, and the stock market goes up the bulk of the time, that's a spurious correlation. That doesn't mean anything. The Super Bowl isn't determining the stock market. And you can say the same thing about a lot of the gun data. There are national trends, regional trends, and there are trends for gun violence. There are trends for guns, and one doesn't necessarily have anything to do with the other. They may be no more causal than the Super Bowl and the stock market, but they happen to move in the same direction. And so when you start analyzing this stuff with a little bit more scrutiny, you don't see all of these same findings that people are turning up, that the lots are turning up. Now, how are we asking this question? Remember, this is just a bunch of epidemiology. And for homicide, it's important to know one variable here, one thing it talks about in the introduction before we go over the methods. In the past 35 years, homicide rates in the United States have moved in cycles. It is not linear. It goes up and then down and then up and then down. It is phasic. It is cyclic. Now, you cannot do linear regression on cyclic data, on non-linear data. That doesn't make sense. You may be able to find significance or insignificance if that's what you're looking for, but it doesn't matter because it's non-linear data. You can't do linear regression on it. That's ridiculous. Now, the types of studies are commonly doing here: cohort and case control. You guys know what that is: a cohort study, a case control study. You guys know how those are done. There's a question about the point of the gun articles is that many of the studies are exaggerating and don't focus on confounding variables. Yes, the studies that are coming out, unless they're saying the gun data don't really lend themselves to this type of analysis, whatever you're saying based on these findings is not supported by the data you analyzed. And so some studies are better than others. But for the most part, people analyze this stuff. They get on the news and they say, well, there's a 15% this or that. And every time this happens, you see this outcome. False, right? There's no evidence of what people see on the news. That's just made up, right? You might as well just say there's 100 billion deaths a year. That's just as true as what people are saying. It's not just as true, but it's just as supported by the literature. And that's what this lab is going to be about, is showing how bad the data are and how they don't lend themselves to the analyses that are being done. Now, case control and cohort, right? Take a bunch of people who have, died of guns and people who haven't died of guns and look back at their exposures. Cohort, take a bunch of people who have guns and people who don't have guns and follow them forward. So sticking with the case controls, people who died and people who didn't die, or people who were in gun violence and people who weren't in gun violence, and look back at what they did. They're like one of the most cited studies, right? This one from 93, one of the most cited studies. The cases, you don't need to know this study, anything about it, but this is just explaining the context of all this stuff. Households in which a homicide happened, cases. right? This is a case control study. We're looking backward. Controls, households where homicide didn't happen. Now, over a 5-year period, let's look backward over 5 years. Cases, 36% had a gun, 23% of controls had a gun. Okay, but remember the type of people who is the gun, was that somehow responsible? Having guns in the house, is that what did it? Or is it just the type of people who are living in these circumstances and committing these crimes are the type of people who would have guns? And as you start looking at the other explanatory variables, there were 55% of people in a love triangle. I mean, so these subjects of the cases of people who are killing each other, where they're like more than half of them are in this like cinematic love triangle. That's more important than the gun, right? And so, 77% of people were killed by somebody intimate, and only half of the homicides was gunshot. The cause of it. So when people start saying a lot of these claims about you have guns in the house and people are going to die, the type of people who are they in a love triangle? Is there some weird intimate thing going on? The gun isn't even involved. They're like strangled and stuff. And so we have to be really cautious. And so they did a logistic regression and an odds ratio from an explanatory hold variables constant kind of way. But the generalizability of these studies very limited, very limited. So from where there are more guns, there is more homicide. When people start making this sort of claim, where there are additional guns, where you're finding more guns, there's more homicide. Think how much New York suffers from these sorts of correlations. How many crimes happen in New York City? Well, a lot. The gross amount, it's a lot. Well, how many people are in New York City? What's the per capita? What's the ratio? What's the likelihood of you being victimized? Well, it's actually not that high because there's so many people. And so if you have a sample of 1 billion people, there's going to be a lot of crime compared to go to like Wyoming and there's like 6 residents in the whole state. Like you go to Wyoming and the crime is very low. You go to New York City and there's just like way more people than there are in the entire state of Wyoming. And so you expect there to be, what you have to look at is these per capita things. And so people say, well, the US has 300 million guns and look how much crime there is. Yeah, but I mean, there's like over 300 million people, and people are sometimes criminals. And so where there are more guns, there's more people. There are more people. And so, 2001, we think there's about 230 million guns. 2007, there's about 270 million guns, depending on what surveys we're using. Get a little bit more current, fast forward the world a few more years, and there's over 300 million guns, roughly the same number of guns and people, probably more guns than there are people in the US. And so it just depends what story you want to tell. US, tons of guns. I mean, just more guns here than anywhere, and high gun-related crime. So if you just want to run a basic correlation, say lots of guns, lots of crime, the US starts to look bad. But then when you start looking at things like, well, gun ownership is increasing, gun crime is going down, it depends what story you want to tell here. Same thing. Let's look at guns per 100 residents. US, pretty high. Right, this is pretty high, and so probably more guns than people, right? And Serbia is high. You get out like Japan is very low, Poland is very low. Well, crime here tends to be low, crime here tends to be higher, and so you can make those correlations, but those are very crude. Now, the databases that will be uploaded. I'll have Nathaniel throw it up this week if he hasn't already by the end of the weekend. There are a couple of databases from the Washington Post that you can find these databases. They're the exact databases that were used in the news over and over and over and over. When people are citing their statistics about gun control, you have the same data, the same analyses that they used. And again, we can do regression analyses. Once you have all of your correlations and you're coming up with these narratives, time to analyze with regressions and tell a compelling story. It's not going to be compelling because the data don't really support that, but you can make compelling p-values and compelling for a linear regression. It's an unstandardized beta. for logistic regression. It's called an odds ratio, or the exponentiation of beta, the odds ratio. But at least do these two. You can also do that one. You open up SPSS, right? We're going to go through how to evaluate quality of data first, and then we'll talk about regression if we have time today. But this is probably your logo. This is old SPSS logo. This is probably what your SPSS logo looks like. Now, what we're going to do is explore. You go to descriptive statistics and then go explore. This is what your database is going to look like. There's a bunch of countries. There's the US and Yemen and Switzerland and Finland and Serbia. You just go down the list of countries, and then there's all these like percentages of homicides by guns, and there's all this. There are all these data points in here, and you're going to analyze this. But the first thing you want to do is know, are the data distributed in such a way where these analyses are sound, or is it just statistical gibberish? Which that's the answer, right? But descriptives, explore. That's what we're gonna do, not frequencies and descriptives. You'll get this information here, but explore. It's a more comprehensive version. And then just take all of these, your continuous variables, and put them in the dependent box, right? You just highlight them. You can highlight them all at once and click the arrow, or you can just click each one at a time and click it over, whatever. You put them in the dependent list. Now, factor list, this is if you want to divide it by something. You don't need to do this unless you create new variables where it's like above and below the mean, or European countries versus non-European countries, or above and below the equator, or you can create your own variables, and those might be dichotomous variables. You could do countries with a population above X whatever, or below X, and code them as 0 and 1. So you might want to do that for your lab, where you create a new variable. Then you can put that variable, since it's a dichotomous or some sort of ordinal or nominal variable, put it in the factor list. Otherwise, just throw everything in the dependent list. Click on the statistics button, hit descriptives, right? So you're going to get your descriptives, your mean, standard deviations, right? Your confidence intervals. So that's the descriptive button. And then click on the plots button. And these are the three options you choose, right? So the histogram over here, the normality plot with tests, and then continue, and then hit the options and exclude cases pairwise. Hit continue, hit OK, and then you're going to get your outputs. Now, I'll show you different versions of outputs of these things. This is the old SPSS. Next week, we'll go over this again, and I'll show you what new SPSS outputs look like. It depends what statistical package you're using, what the SPSS outputs are going to look like, but they're all the same information. The reason I'm doing this is I want you to not rely on one particular aesthetic look of the data, because you're going to have to understand what the data mean, not just like, okay, here's the box I'm expecting, and you want to know what the words mean, and you want to know how it's organized, and so I'll show you a couple of different versions of the outputs. But the first thing, case processing summary, this just tells you what you looked at. Right, this is just what you analyzed, and some of these you're missing data. Total homicides by guns, homicides by 100,000 people, whatever. You're missing data on 9 countries, but there are 185 countries in this database, and these two variables you're missing. 9 of those countries don't have data. That's all that's saying. Descriptives, you know this stuff. The mean and the standard deviation. So the mean for guns per 100 people is 10.2, so about 10% of people have guns worldwide, plus or minus 12.1, so about 10.2, 10.2 plus or minus 12.1. That's the number of guns people have. Now, your mean and median, you'd like to see those pretty much equal, around the same number. This is not going to be exact, but you'd like to see them kind of similar. The median is a little bit smaller than the mean here, and so what we're seeing is some Bill Gates here. We're seeing some countries that are skewing the data, some countries that are like very high, and it's affecting that mean. Guns per 100 people is like the US. Now, the next thing to look at is the variance compared to the mean. So the mean is 10.2. Remember, we did that example of that 84% average test, and I just came up with 10 exam scores, and we came up with that average, and it was 84%, and we just did, we added them all up and divided by 10. And the variance and the mean were both 84. There's nice distribution. And so what we see here in the gun data, and this is a problem, the mean is 10.2. The variance is 146. this is silly, right? This is ridiculous. So you want that mean and variance to be pretty similar. They don't have to be exact, but you want them to be in the range. You want them to be kind of close to each other. And so there's what's called over dispersion or under dispersion. Over dispersion, you're seeing this exactly what this is. This ridiculous variance over the mean. It's called over dispersion. If it were the other way around, it's under dispersion. Often over is what you're going to encounter. And you can just look at the minimums and maximums. And again, in the outputs, there's going to be, so this is just guns per 100 people. The next one, number of civilian gun deaths, and it starts over with the means and medians and stuff. And then there's going to be the next one, the percentage of people killed by guns or whatever. So it's going to go through every single variable one at a time and give you all of these outcomes for each one. So look at the minimum maximum. So guns per 100 people, the minimum is 0.1. I mean, there's very few guns per 100 people. The maximum in this database is 88.8. So we're looking at like the US at this time was close to 90 guns per person. Now it's more than that. So if something's weird, you just want to notice that. Now that's a really wide range, but it doesn't necessarily mean that the data are not well distributed. But when you look at skewness and kurtosis, that gives you more information. Skewness, 2.6, kurtosis, 10.6. So you want those to be between -1 and +1. Both of those, just have them between -1 and +1. The closer to 0 they get, the better bell curve you're going to have, the better distribution of your data you're going to have. Will somebody be my time? You got 5 minutes left or whatever. But so skewness and kurtosis, if it's a negative skew, if you see -3 is the skewness or something, it's got 15 minutes, thanks. You're going to see this left tail, this negative tail. Now skewness, -3, it's not the direction of the peak, right? It's the direction of the tail. So if it's a negative skew, you see the tail dragging off in the negative direction. If it's a positive skew, if skewness is like, 2, 3, 4, you're going to see this tail dragging off to the right. So that's what skewness is going to look like, where you're affecting the bell curve. What you want is a beautiful bell. You want to like be able to play chimes on it. I mean, you want this nice, pretty Liberty Bell. And when you start getting stuff like this, it starts to mess up your analyses a little bit, the trustworthiness of your analyses. The other thing you need to look at is the kurtosis, which is the peakedness of it. So if it's platykurtic, think like plateau, platy, a platypus with its like flat bill, a platykurtic. It's not steeped, right? It comes up and sort of levels off, and there's all this kind of middle ground. This is your normal distribution. That's what it should look like, right? Leptokurtic, like leptothin, like leptin, the hormone, the satiety hormone, and like you're going to get thin on this. It's not really how it works, but leptokurtic means this slender, this thin, the slender. And so as soon as your distribution starts to look ugly, not that these are like ugly aesthetic, but as soon as it's not the pretty, it's just not like a Liberty Bell anymore, we start to encounter some potential problems. Again, just looking at the skewness, the negative skew is all of the data over here. What we want is that nice, that might actually be a little bit leptokurtic like this, but what we want is a nice bell. And when you start skewing negative, your skewness is -3 or something, or skewing positive, your skewness is like +2, 3, 4. That's what it's going to look like. Now, another box, the tests of normality. There's these two different columns of significance. If you're going to do like the Smirnoff Ice, right? If you're going to do this one, huge samples. You're doing, this isn't a huge sample. I mean, we're talking like you're doing epidemiology, population-based surveillance, tons of people. I mean, that sort of thing, use this significance. If something like this, where you have a sample of 180 or whatever this is, 185 or something, then just use the Shapiro-Wilk. But here, if P is greater than 0.001, it's close. It's fine. You don't need to be like, oh, 5. As long as you're seeing numbers here, if you're seeing numbers, that's encouraging. When you look at just zeros, right, that's okay. You have a problem with your data. And so that's what you look at for the tests of normality. And you can say, well, there should be a Wilk for each one of these variables, right? For guns per 100 people, nope. Number of civilian gun deaths, nope. total homicides by guns. Nope. Like none of them look good here. And you can report that. Now, the histograms, that's what you clicked on. That's one of the options you clicked on. This is what it's going to show you. And we have skewed right? It was a positive skew. Remember the skewness, 2.6 or whatever? I mean, like, what do you see something like this? And so these are just the frequencies of value. So guns per 100 people, there's us, right? There's the US over here. If you're in the US right now, if you're COVID lecturing from home somewhere else, then maybe you're over here somewhere. But here's Stockton, but this is not this is not a nice bell, right? It starts like super high and then just tapers to the right. That's not a nice distribution. And then you get these QQ plots, these quantile plots. I talked about this earlier when I was showing you our exam score, and I have the QQ plot from our exams. Now you don't need to really even understand this. From the perspective, I'm not going to put QQ plots on the test. But these are going to come up in the analyses, and what you want to do is look at it. Just look at this, and it looks ridiculous. What you want to see is these little dots follow the line, right? That's what you're doing. Now, remember these quantiles, when we were talking about quintiles, fifths, right? Quartiles, fourths. When you're doing a lot of epidemiological work, you separate people into quantiles and quintiles, and the top 20% of people and the bottom 20% of people. And you all know what percentiles are, because if you've taken the SAT, you're in the 80th percentile or whatever. Which means you separate everybody into 100, right? Percentage is 100. So these percentiles into 100 evenly grouped groups. So with quartiles, there's the same number of subjects in each group as the bottom quarter, and then from the bottom up to the half, from that halfway point to the half, and then from the median, right? You got the median is a quantile, is above and below. It's half the people are above, half the people are below. Quartiles is evenly distributed, and so this is the expected and observed quantiles. They don't track the line at all. I mean, it just looks hilarious. I mean, this is last semester's grades. Track the line pretty well. Here's guns. You can't analyze this. You're not going to get trustworthy findings. Here's is even a little bit better, our grades from this semester. Tracking the line. And again, I'm going to show you different types of outputs. So I'll show you what the graphs look like next time we go through this. I'm going to show you SPSS 26, but you don't want to get used to any one output, because just every couple of versions of SPSS, everything changes. And so you don't want to get used to the aesthetics and then encounter something new, and you can only play when you have home court advantage, right? You want to be able to play when you go to any stadium. Yeah, you don't want to go to the opposing team stadium and not know how to hold your bat anymore, right? So you want to be able to encounter a bunch of different outputs and be like, okay, I get it. What I'm looking for is an R squared. What I'm looking for is an unstandardized beta. What I'm looking for is an odds ratio or an exponentiation of beta. What I'm looking for is a Pearson correlation coefficient. What I'm looking for is whatever. You want to be able to find those things in the outputs, and you don't want to rely on home court advantage to do it, where it's like, oh, this is not the format I'm used to. I'm no longer capable of reading statistics. But so this is this year's grades. This is our first exam. It tracks the line pretty well. Our quintile expectation and what we observed is pretty similar. This is guns. That's not what you want to see. Now the box and whiskers plot, I'm not going to make you understand this on a test either. I'm not going to make you report this. But to understand what this is, the interquartile range, I'll show you what that is in just a second, but you know what quartiles are, divide by 4. So the interquartile range is just the middle two. But 3 times the interquartile range, these are the asterisks, right? So this is like massive outliers. When you have these giant outliers, it messes up your data. The outliers drive your outcomes, not the stats. Not the distribution, but the outliers are your findings. And so the interquartile range, right? The quartiles right here. And so the interquartile range would be in here, or the middle 50%. And so if you're 3 times outside of that, I mean, we're getting into some serious outlier territory. Now, if you want to see the charts, I actually prefer Excel. I don't like, but I do like it for some things. The visuals, Excel does visuals better than SPSS. But if you want the charts from SPSS, and every single version of SPSS does get a little bit better in the visuals, but still Excel is better for this. But graphs, chart builder, click on that. And then you just click on scatter or dot over here, so the scatter plot, and just drag in your X and Y and hit OK, and you'll be fine. It's very easy to do, and you'll get something like this. It's not a particularly pretty graph. This is silly, right? So guns per 100 people, homicides by guns. And so up here we have the US, right? Brazil all the way over here. Brazil doesn't have that many guns, but homicides, they're really leading the pack. Great rainforest stuff. So like we see these massive outliers, and like this is just silly, right? You can't analyze this. What does our regression look like? Our linear regression, where we're trying to come up with some prediction model, is probably going to do like this. But that doesn't make any sense off of this, right? You can't come up with a prediction that way. And so going back to some of these ideas of what is a correlation, remember, do your bivariate correlation tables and drag all this stuff in. This is the database that you're going to be using, right? So take all of those continuous variables, scale, right? They have these little ruler icons. Take the scale data, drag it all in over here. And then if you want, you can do options and click on means and standard deviations. And this is going to give you the descriptives at the same time. So if you don't feel like running your descriptives first and then doing bivariate correlations, you can do them at the same time. Just click on options and then click on that. Hit continue and then hit OK, and you're going to get your descriptives first, means and standard deviations, number of civilian gun deaths and standard deviation, number of total homicides, standard deviation. Now these standard deviations are sort of silly. On average, it's close to 700, but give or take 3,200. I mean, this is not what data look like. And then we get our correlation table, and notice this looks a little bit different from the previous one. 5 minutes, thanks. This looks a little bit different from the previous one, right? This is an older version, but it's the same information, right? It's the same information. So it depends what version of SPSS you're running. Civilian gun deaths, the Pearson correlation coefficient, right? So we see positive. That means as one goes up, the other goes up. Nothing. Positive, as one goes up, the other goes up. Or you could go down, total homicides by guns, and does it relate to homicides by guns per 100,000 people? Yeah, as one goes up, the other goes up, right? So you're just linking these two variables. And if you just look, like, let's look at these two. So number of civilian gun deaths, does it correlate with total homicides by guns? Yes. Now this doesn't tell you much about prescriptive, like, well, with each additional homicide by guns, the number of gun deaths, well, you'd expect those two to move. This just tells you that they do move, p-value of less than 0.001, but that's getting to an R value, to a Pearson correlation coefficient that is worth acknowledging. Homicides by guns per 100,000 people, there's just nothing there, right? The Pearson correlation coefficient is less than 0.00. I mean, there's just no correlation here. The p-value is almost 1. So there's nothing there. Go down here, guns per 100 people. Does it relate to number of civilian gun deaths? Yeah, pretty strongly. An R value of 0.524, p-value of less than 0.001. So there's less than a 0.1% chance you would have observed a correlation this strong or stronger. Over here, not much going on. P-value is insignificant. It's positive, the correlation, but it's insignificant. Over here, negative correlation, but insignificant. And over here, positive correlation and significant. So there's a 0.9% chance we would have observed an effect this big or bigger, of this magnitude or greater than that, if the null hypothesis were true. But remember, these data don't really meet the assumptions for a lot of the regression modeling, and they just don't have distributions where you get to analyze it and take your results seriously. So if we're just doing Pearson correlation coefficients, right, we have Mocker area flats, right? We have this little spot that I talked about earlier. You're dropped into a new environment and you try to get your surroundings. It's like, all right, what's here? Like, what am I looking at? Where are the streets? Where is the grocery store? Where's the gym? Where's the school? And you're just getting these basic ideas of like where the roads go. Now, if once you start finding these correlations, it can guide you. You can say, okay, I get it. The number of civilian gun deaths and guns per 100 people. Okay, that's something I can look at. I can look at a regression with these two and see if there's a story to tell there beyond the basic correlation. Guns per 100 people and percentage of homicides by guns. also significant. So let's explore that, not with correlations. This isn't the end all. This isn't where you stop. You explore it with regression. So let's do a regression with this one. Simple linear regression is essentially the correlation, but with more information. You get an unstandardized beta. If I know X, can I predict Y? If I know my predictor, if I know the value of an independent variable, can I predict the dependent variable? And so to run a regression, you go analyze regression, right? And then linear or binary logistic. Those are the only two I'm going to have you run this semester. Now we're going to talk about negative binomial, but we actually run that elsewhere. I keep hearing voices, so just make sure you are muted if you weren't. So linear and binary logistic. For linear regression, this is if you have a continuous dependent variable. If your dependent variable is continuous, you use a linear regression. If your dependent variable is binary, 0 or 1, right? It's yes or no stuff. It rains, it doesn't rain. That would be a logistic regression. But predicting a continuous dependent variable, that's a linear regression. And so if you use your independent variable, guns per 100 people, and your dependent variable, number of civilian gun deaths, we can actually just say okay right here. Now, you'll probably want to click on statistics and click on the 95% confidence interval. That's really the only thing you need to click on. And then you hit okay. And you're going to get a few boxes. And this is the last thing I'm going to show you is these 3 boxes. So in R squared, this is telling you what percentage of your scatter of your dependent variable you're explaining by your independent variable. In this case, there's one independent variable because it's a simple linear regression. If you have multiple independents, multiple predictors, it is a multiple linear regression. It's still a univariate analysis because there's one dependent variable. It's not a multivariate analysis, which would say 0 minutes. Okay, would just say multiple dependent variables. But really quickly, very last slide. Feel free to log off if you want to get out of here, if you have somewhere to be. But what you're looking at, this is just the overall significance of the model. And this right here, guns per 100 people, with each additional gun per 100 people, you are predicting 909,709.3 additional civilian gun deaths every single year. P is less than 0.001 with each. So you go from 3 guns per 100 people to 4 guns per 100 people. That's like 1 million additional gun deaths every year. Now, what happens if you go from 10 guns per 100 people to 20 guns per 100 people? Okay, now we have over 9 million additional gun deaths. The problem is our starting point is negative 5.5 million deaths. So if we just have no guns, we revive 5.6 million people every single year. This is how it gets so ridiculous when people are making these claims. Okay, so we'll end there. And on next lecture, right, next on Monday, we'll start with regression. We're going to drop a lot of that scene setting, the scenario of school shootings and stuff like that. We're done with all of that. And we're just going to start with regressions, and we'll do a bunch of linear, and I'll go step by step through linear and the explanations of what the outputs mean. And then we'll go into logistic. And with logistic, I'll do old outputs and new outputs. But I will start with new outputs for linear regression next time. So you can look at multiple versions of what it looks like. Any questions for today? Everybody it's Friday. Everyone's just exhausted. Me too. All right. I will see everyone after the weekend. Go sleep and whatever.